In these sections, I'd like to explain the Cauchy-Euler equations. The following linear differential equation is known as Cauchy-Euler equations. Before the nth derivative of y with respect to x, we multiply the x to the n. So n minus 1's derivatives, we multiply the x to the n minus 1's. A sub n and a sub n minus 1 is a constant values. For the first derivative of the dy dx, you multiply the x and the a sub 1. The non-derivative of y, you multiply the a sub 0. So this is Cauchy-Euler equations. So as a second order differential equations, you could write ax squared, second derivative of y with respect to x, plus bx times dy dx plus cy. This is second order Cauchy-Euler differential equations. And a, b, c is a constant values. Then this equation is transformed into the second order differential equations with a constant of a, b, c by changing from the x to the t using the x equal exponential t. So this means t is expressed log x. So this means dt dx becomes 1 over x. Then we'd like to change the first order derivative and the second order derivatives. dy dx using a chain rules is expressed dy dt dx. So we can use this formula dt dx equal 1 over x. This is 1 over x dy dt. So from these equations, x dy dx is turned out dy dt. So second terms of the first derivative dy x times dy dx is expressed the dy dt. And second derivative is expressed d dx. And first derivative becomes 1 over x dy dt. You substitute this into the here. And the derivative is minus 1 over x squared dy dt plus 1 over x. So derivative. And chain rule we apply it. So this is second derivative with respect to t. dt dx, you can use these relations. So it becomes minus x squared dy dt plus 1 over x squared second derivative of y with respect to t. So from these equations, you can express x squared second derivative of y with respect to x equal second derivative with respect to t minus dy dt over this relation. So this corresponds to the first terms, these terms. Then you can substitute this into this differential equation by changing the variable from the x to the t's. So ax squared second derivatives plus bx dy dx plus cy equals 0. So it becomes a minus dy dt plus b dy dt plus cy equals 0. So now it becomes a second derivatives plus b minus a dy dt plus cy equals 0. So we have a differential equation with a constant coefficient So this is exactly same with this equation. Okay, once we have these equations, I have shown you how to solve this differential equation by substitute y equal exponential mt, and it becomes a m squares plus b minus a m plus c equals 0. And you can find the solution of the m. We have three forms of the solutions in case of the distinct real roots, or repeated real roots, or complex root. So this is a method I explained, but in this case we have to transform from the x to the t using the x equal exponential t. Or you can substitute y equal x to the m into the Cauchy-Euler equation to find the exact same equations for m. am square plus b minus am plus c equals 0 by substitute y equal x to the m. Once you have an equation for the m, you can substitute into the power index of the m. You will get the answer. Okay, also if you know the x equal exponential t, so from this y equal exponential mt is exponential t to the m, and the exponential t is equal to the x, so this is x to the m. If you want to solve the Cauchy-Euler equation directly from the equations, you can substitute y equal x to the m. Or you can change the variable from the x to the t using the x equal exponential t to have a differential equation with a constant coefficient. Then you need to substitute y equal exponential mt to find the solutions. Okay, this is the end of this session.